This is Unit 4, Video 12. We will finish up the unit talking about some special types of synthesis and decomposition reactions. So these will be reactions that are a little more complex, essentially a combination of the reaction types that we've seen earlier. So let's take a look first at synthesis type reactions. If you have a metal oxide and you combine that with water, what you'll get is you will get a base, a strong base, or a metal hydroxide. In this case, the base is going to be the hydroxide. And an example of this would be sodium oxide added to water to produce sodium hydroxide. The balanced equation is written for you right there. Now this could be substituted with any metal, so you can put potassium in here, you can put calcium in here, barium, really any metal you'd like. The same reaction results. Usually we limit this to group 1 and group 2 metals, but you can also put iron if you want in here, and iron oxide will technically produce an iron hydroxide. The same thing happens with nonmetal oxides. If you put a nonmetal oxide with water, it will give you an acid. Now, an example of this would be carbon dioxide, which is a nonmetal oxide placed in water to give you carbonic acid. Remember, this is carbonic acid. Now, you can again substitute the carbon with sulfur or with chlorine or with any other nonmetal, and a similar result will occur. We'll show you some nonmetal oxides that are a little tougher to see this happen, but it'll happen the same way. Both of these are synthesis reactions, and in this case you can literally see how carbon dioxide and water combine together. So if you think, for example, that I'm sticking the water molecule right on top of the CO2, essentially I put two hydrogens and an extra oxygen in there, and that's how I get H2CO3, carbonic acid. It's a little harder to see the same thing happen with a base, with the top reaction, but really it's the same thing happening. The H2O comes on top of it, and technically what you get is you get 2 sodiums, 2 hydrogens, 2 oxygens, but the ratio is NaOH. So hopefully that makes sense. Now, with nonmetal oxides, it could get a little tougher to see what the acid would be. In the case of phosphorus, for example, the phosphorus comes in 2 varieties, or phosphorus oxides come in 2 varieties, P4O10 and P2O3. And what happens is they form the 2 possible phosphorus oxide acids, which is phosphoric acid. Remember, this is phosphoric because you have phosphate, 8 becomes ic, and then here you have phosphorous acid. Now, the way to figure out which one it'll be is to actually take a look at the oxidation number. So here it says, to help you predict which oxyacid forms, look at the oxidation number. It should be the same. It's important to understand that in this reaction, this is not a redox reaction, so there is no oxidation number changing. So if you analyze here, for example, phosphorus, we have 10 oxygens. Each oxygen, remember, is -2. If we have 10 of them, we have a -20 on the oxygen side. We must have a +20 on the phosphorus side because the whole thing is 0. And so we have +20 divided by 4 phosphorus. Each phosphorus is +5. Now if you analyze the phosphorus in phosphoric acid, remember you have hydrogen is +1, so you got +3 since there's 3 of them. Each oxygen again is -2, you got 4 of them, so that's -8. The whole thing is neutral, so phosphorus here must be +5. Notice they match, and they should match, and that's how you'll figure out that you've got the right acid forming from the initial oxide. If you analyze this phosphorus, you can take a minute to analyze this phosphorus and this phosphorus, you will see that they have the same charge. And the charge should be +3. Alright? Now, because they form bases, because metal oxides form bases, they will react with acids to form salt and water, which is simply a neutralization reaction. So you take a metal oxide, in this case again sodium oxide, add it to an acid now, and you have yourself salt and water. This is a little hard to see from this angle, but if we realize that what we just talked about is that metal oxides in water produce metal hydroxides, NaOH, we can then see how NaOH reacts with HCl to form salt and water. So really this is a simple neutralization reaction, which is a double replacement reaction. The sodium and the hydrogen simply replace to give you sodium chloride and HOH. The only thing you have to realize is that sodium oxide technically behaves like sodium hydroxide. And the reason for this is because you're putting the sodium oxide, yes, it is a solid, but you're putting it into an aqueous solution, which means it hits water. Aqueous solution, remember, has water in it. So effectively, sodium oxide is being added to water first, becoming the hydroxide, and then we got the double replacement reaction to give you a salt and water. And then the same thing happens vice versa. If you're beginning with a nonmetal oxide, in this case CO2, you can react that with a base to give you the same salt and water. And again, the way to think of it here is CO2 can actually be thought of as H2CO3, carbonic acid, from the previous slide. And again, if this double replaces, you'll get your standard or your typical acid-base reaction to form sodium carbonate and water. All right, so we'll try one or two of these. Oh, by the way, for the same reason, here CO2 is a gas, but it is hitting an aqueous solution, which means it's being added to water. And the previous slide said that if you put a nonmetal oxide in water, you get the acid. Okay, why don't we try a few of these. Here it says write the balanced chemical equation for the reaction of aluminum oxide with water. So this is going to be the synthesis reaction. Remember, aluminum oxide is written as Al2O3 because of the charges. You always have to balance the charges when you're writing these ionic compounds. And we're going to add it to water. Now, here we have a metal oxide plus water. What does it form? It forms a metal hydroxide. So we'll actually write aluminum hydroxide. Aluminum hydroxide should be AlOH3 because hydroxide, remember, has a -1 charge. And this is the equation. Now, make sure you balance the equation. It looks like we have 2 aluminums. Let's double that up. It looks like that gives us 6 oxygens on the right side, and we have 3 from the aluminum oxide, 3 more here. 6 hydrogens gives us 6 hydrogens. We are balanced. For state symbols, obviously water is a liquid. Aluminum oxide or all metal oxides are ionic in nature, so they will be solids to begin. Remember, all ionic compounds are solids. And then if you put those two together, you get an aqueous solution, since you have yourself a solid plus a liquid, which is the definition of dissolving. So that's how you get an aqueous solution. All right, hopefully this made sense. Go ahead and try one on your own. Try a nonmetal oxide added to water. And then let's do example 21. This one's going to be a little more involved. Write the balanced chemical equation for the reaction of sulfur dioxide with aqueous sodium hydroxide. So if you tried the equation above for sulfur dioxide, now we're going to add it to a base. So sulfur dioxide is SO2, sodium hydroxide, NaOH. So in this case, what we have is a nonmetal oxide being added to a base. Now remember, the nonmetal oxide becomes an acid when you add it to water. This base, here it says aqueous sodium hydroxide, so this base is aqueous, which means technically the sulfur dioxide is hitting water, becoming H2SO3. This is the product of the equation that you should have seen right above in problem 21, or example problem 21, or rather 20, practice problem 20. And so what you have effectively is it's not this compound that's reacting with sodium hydroxide, it's actually this compound that's reacting with sodium hydroxide. You still write SO2, but you realize that it's H2SO3 that's reacting with it. And this just gives us a standard double replacement between hydrogen and sodium, and so you get yourself sodium sulfite. This is SO3 is sulfite. Now sodium sulfite, SO3 has a -2 charge, just like sulfate does. So you get yourself Na2SO3. And the other product is HOH, which is good old H2O. Now, technically you shouldn't cross it out. I just kind of crossed it out just to show you that it's really this compound down here that's reacting, but you will keep it as SO2. So you can think of this as the reactant in parentheses, the one that's really reacting. And then make sure we can balance the equation. It looks like we have 2 sodiums on this side and that gives us 2 hydrogens and 4 oxygens, which completes it. Also, let's put in the state symbols. Now, sulfur dioxide is going to be a gas, and here it doesn't say so, but your nonmetal oxides are typically going to be gases, or a lot of them will be gases. And then sodium sulfite then should be aqueous, and water is a liquid. So it's the same thing as we've seen before, salt and water. The salt is always aqueous, unless it's not soluble. Remember, you can use the solubility rules. Because we have sodium, which is a group 1 metal ion, this will be aqueous, this will be soluble. And that completes the equation for us. So a little more involved, but really this is a neutralization reaction, just from a different perspective. All right, that will finish up video 12.